Okay. What would you
Can
like?
you go over the integral test?
Yeah, absolutely. All right. Let's do maybe a bigger problem that
Okay.
involves that kind of like the stuff on the fake test. Does that sound okay?
Yeah.
Okay, cool. So, determine if try to get a good one here. And then absolutely is the second question. So we got two questions here. First one is, does this alternating series converge? And then does it converge absolutely? And let's say on absolutely, let's use the integral test. So first off, let's just start with the basic one. Um, I'll tell you on the test, but do you know what test I would use just on this series itself?
Alternating series
Yeah,
test.
perfect. Awesome. So we're going to use the AST and we're going to identify the non-alternating part. So we got that. And does that make sense?
Yeah.
Yeah, cool.
Mhm.
Then sounds like we got more. We got Lou. Hi, Lou. Um, so then this is decreasing, and that's always going to be the case. But can you see that this is decreasing because as the bottom gets bigger, the fraction gets smaller? So if you
Right.
yeah,
Yeah.
right. So it's
Mhm.
decreasing, check. And then is this true? Does a sub n go to 0?
Yes.
Yeah, agreed. Because you got a fixed thing over a thing blowing up. So we're good to go on that. So by the
Mhm.
AST, it converges. And so now we'll get to the actual question you had, which is when I consider the absolute version of this, so does it converge absolutely? We look at this series. And Lou, just to bring you up to speed, Vivian was asking about using the integral test. So I made it a bigger question than her question, but now we're about to use the integral test here. So basically all you do is you essentially replace the integral sign or the sum sign with an integral and the n with an x, or you can leave it as n if you want, but I think our brains maybe work better with x's in those integrals. And so does that setup make sense? Like at this point? Okay, awesome. And so what I
Um.
need to do though is find this integral. Do you want to try that? Do you want to maybe both take a moment to work that integral through?
Yeah, but do we have to
Yeah.
prove that it satisfied the condition, positive, um, like the
Oh,
function f of x being
yeah. So in like out in the wild, definitely. And the key thing
okay.
is it needs to be a decreasing positive function. And you can
Hmm.
see that this. And we kind of actually answered part of that question up here when we decided it was decreasing. And it'll always be okay to use the integral test when I ask you to use it. So that's I wouldn't worry about I appreciate that you're thinking about that, but no,
Okay.
you don't. So maybe you could both just give this a try and see what you remember about cranking out them integrals. Awesome. I'm gonna be right back with more fun. just not to spoil the surprise, but to let you know what you should get. You should get 1/5. You get that thing worked out properly, I believe.
Wait, how did you get 1/5?
Well, I just did it in my head, but I'll show you. So, and then so I would first convert this to a power like that, and then do this. Oh, B, make that a B. Okay, is that making sense so far? Just the setup? Okay, cool. So then power rule on that. So oh, it should be 1/4. Sorry. I think it should be 1/4. So much for doing it in my head. Not great. So when I do the power rule, it's x to the -4th, and then the -1/4 comes out in front. Like that. Oops. Is this looking better? Yeah. Cool, cool, cool. And then we finish up here, plug in the B, plug in the -1 or the +1. And then let me just rewrite this a little bit more so it's a little more obvious what's going on. So like that. So, and let me know if that's making sense. Yeah, cool. And then,
Because
yeah, go ahead.
because that one goes to 0, and then
Beautiful,
it's
Lou.
just 1/4.
Absolutely. Yep. Because you got a fixed thing over something blowing up. So nice. Does this sound good?
Yeah.
All right, cool. So, did you want to do
So
more
would it
practice
converge?
like that? Oh yeah, sorry, we got to finish it up. Thanks, Vivian. Yeah. So, since this integral converges, the series converges. Absolutely.
So you just assume that the integral acts the same as the sum.
Yes, absolutely.
Okay.
And so that series, that original series that we had, this alternating series, when we looked at the absolute value, that converged. So this is absolute convergence, not conditional. Maybe we can take a look at another one here, to just see another side of this. The series converges. Absolutely. Let's actually put that in there. All right, so how about another one? Let's try this one. What about this series? And this is going to be the cube root of n. And then, sorry, yeah, okay, go ahead. Just use the integral test on that and see what you think. You can tell by the p series that you can tell what it's going to do if you recognize the p series, but let's just practice the integral test.
So would it diverge?
It does. Yeah, absolutely. Yep. Does that sound good to you too, Lou? Yeah. Cool. Let me finish just working it all the way through just because I got to kind of like
Okay.
I just have to do it now that I've started. And it's a good way to just make sure everything's in line in your own. And last time I took a guess and that didn't work out so hot. So this is going to go to the 2/3, and then I bring a 3/2 out in front like that. 1 to B. And then plugging in the B. Got 3/2 B to the 2/3 minus 3/2 times 1. And this piece blows up. So divergence. How we feel about that? Awesome. Yeah, cool. What else would you like to talk about? I mean, I've got a list of problems too. We can just work. So if you don't have specific things, but I wanted to make sure to answer anything you wanted to talk about first.
I do.
Cool.
So
Easy.
I look through the web work, like the final exam review for web work,
Yes.
and I don't know how to do number 10.
Okay, let me go get that.
Okay.
Yeah, let's go there.
Something about Taylor series.
Oh, that's important. I'm glad we're going to talk about that. I got a bunch of those to talk about. Let's see here. So this is the final exam, the web work portion or the exam review portion? Oh, wait, never mind. Sorry. That's an old thing I never released. That doesn't exist. It's you can't
Okay.
see that. Okay, cool. So we're here. So number 10. Let me look exactly at yours. Oh shoot, I'm looking at the wrong homework. What is this called? Is this called final exam review series? Is that the one? I think it sounds right. I think that's right. Okay, this one looks better. Everybody had finished the other one I was looking at, and that would have been cool, but unbelievably shocking. So this looks more reasonable. Why do I keep going to that one? Okay, so here we go. This looks right. So why can't I find yours? There we are. Okay. Well, you're almost done. You're almost done with it. So
Yeah, I only have that one last problem.
okay, okay. So let me show you a cool way to do this problem. I'm going to show you both a cool way to do this problem. So the problem, and I'll do one like it. So this is 10-ish. So find the Maclaurin series for f of x equals, and we'll do like x squared over 1 minus 2x. So there's like the painful way. And this might have been what you started on, and it can get really rough where you crank out all the derivatives.
Yeah, I did.
Yeah. So, Godspeed to you, but let me show you an easier way.
It was painful.
I'm sorry. Yes, it seems like it would be incredibly painful. So for this one, we have those basic series that we talked about. So we've got like e to the x is this, right? And then we had a sine and a cosine and all that stuff. But then we also had, I think I put this one up, the geometric series. Like that. And that's valid when the x is less than 1. So just notice that's just a geometric series with common ratio x. If you look at the actual series itself, right? Multiply by x to get from term to term. And that's the sum formula. First term over 1 minus the common ratio. This is a great formula to know for just all sorts of reasons, but it's going to help us do this problem really slickly. So one thing you can do is you can think of these formulas like this, that x can be anything. So really what it's telling me is that this is the rhythm that that thing on the left is equal to. I don't know why the boxes are getting bigger too. They're almost growing with their exponents, but that's just me being wacky. So if no matter what I put in that box, this is true. So if I put say a 2x in here, and I put that everywhere, then I've got the formula for 1 over 1 minus 2x. And so look, I can check that out. I'm going to simplify it a little bit. Notice how those exponents kind of work like this. So let me know, is that making sense? And do you want to talk about it? Vivian, sound good with that? Lou, do you see where yes, go ahead.
There's the square on the actual number, like 2 squared and then x squared.
Yes.
Are we treating the box as like a parenthesis?
Yes. Yeah, exactly.
Oh, okay.
100%. Yeah. So it's whatever. Yeah. So exactly. That box is basically just a fancy parenthesis.
All right.
Yeah. Cool. Good question. So now, do you see how I can get the thing that I want from here? How do I move from the thing I just did to the thing I want? Because I'm almost there.
What do you mean the thing that?
Okay, so here right now, what I've got is this 1 over 1 minus 2x, and I have the series expansion for that.
Right.
What is it I want? I want x squared times that. So I just multiply by x squared. So in other words, multiply by x squared, that expression, and I've got 1 times x squared, 2x times x squared. 2 squared x squared times x squared just gives me 2 squared x to the 4th. So I'm taking this thing here and I'm just multiplying it by an x squared. Every term gets multiplied by x squared. And now I got this thing. And I just cranked out the power series without doing a single derivative, which is, after, especially as a person who has suffered on this problem, that's pretty slick, right? That is pretty nice. So then we still have to convert it. Oh, and let me help you with some other stuff here. So the radius of convergence. Notice how this formula here, and so Lou, again, that's going to be a parenthesis. That formula is valid when the thing, the common ratio, is less than 1. So what do we have in that box? We have a 2x in there. That's what we put in the box down here to get that series. So in other words, we have 2x less than 1. Well, what does that say about x? That says x is less than a half. Does that make sense? So you can tweak, you can take this formula, and then your problem's similar. It's very similar. It's not a 2, but you got a 3. So Vivian, Lou was shaking her head. She's got that. What about you, Vivian? Does that make sense?
So the x is like for the function to be true.
Yeah, yes, for that series to converge, right? So here, let me,
Okay.
yeah. So this expansion here is only valid when that thing that's in that box is less than 1 in magnitude.
Okay.
And here that's a 2x in this problem that I'm doing. So that would say that x has to be less than 1/2. And that gets me my radius of convergence is actually 1/2 when I replace that x with a 2x.
Okay.
Yeah, kind of. Yeah, maybe.
Yeah.
Yeah. Okay, cool. And so then I've got the series. So like this one down here, they actually asked for the general form of it, which is really hard. I'm not going to do that on the exam, at least not for credit, maybe extra credit or something. But so let's take a look at this series down here. So this is going to be sum n equals 0 to infinity. So if this is the 0 term here, so this is 0, this is the first, this is the second, it looks like x is just the index plus 2. I just should say x to the n plus 2, because notice here when it was 0, it was x squared. When it was 1, it was x cubed. When it was 2, it was x to the 4th. So just add 2 to that index. And then the thing in front is a power of 2. So it's 2 to the, actually it looks like 2 to the n, right? Because this is 2 to the 0, this is 2 to the first. So that worked out pretty slick. So this is what they're looking for, I think, in that first one. Something like that anyway. What you have to do will be very similar to that. So that's kind of cool. I really like that. I love using that geometric series. I think it's really fun. So your mileage may vary.
And then like on the second half, it asks for very, very large values of x.
I'm not seeing that. Where on problem 10?
Yeah, like there's like the first half,
Oh,
and then it's like a
there's
second half.
more. Yes, I see now. Oh shit.
It's a big problem.
Oh shit. Oh, I don't want that in there. I didn't see that second half. Vivian, you're really good at finding stuff I don't want in the homework for me. You kind of always are getting in there. Okay, so hold on, let's see.
But it's like not count towards upgrade, right? It's like
Oh
a extra
no,
credit
not at all.
thing.
But I don't want people to like get hung
Yeah.
up on it, But I don't even understand really what they're.
Maybe we can just skip that.
I'm just gonna delete it. About that. I know you spent a bunch of time on it, but that's it. It doesn't count.
Not really.
Okay.
I mean, I look at it. I look at it for like
Okay.
15 minutes, and I just quit.
Okay. Cool. I am going to delete that. I might
Yeah.
put another one in there, but since it doesn't matter, I can toss them in and out. Hold on. Let me edit this really quick. Thank you for finding that. Good for you.
Good for
That'll
me.
be great. See, I can add that. There's another good letter of recommendation story. So
Thank you.
there you go. No, that's good. It's a good one. Okay, is that pretty much it for you? There's
I
only
mean, I still have like,
Hmm.
yeah, not in terms of that. But I went through all of your for the practice problems that you
Yes,
put in, and I had like several questions. But
fantastic. That's great.
if you want, if you want to go over any stuff that you want to first.
Yeah, that's never a bad idea, right? Like let the person writing
Yeah.
the exam talk. Just let them talk. That's smart. Hold on, let me just get this deleted. Okay, good. You just saved everyone. Great deal of stress. All right. Yeah, okay. I mean, we have time and we've got another hour. So if you want to ask some questions, I definitely like it might be good to talk about them because then I can say like, oh, don't worry about that if it's too crazy. And I'll edit everybody. But why don't we just take your questions? Then don't worry, I'll take time to give you a brain dump of what I'm thinking about.
Okay.
Okay. Yeah.
Yeah. Let's see. Lou, you wanna go first or
I think Lou split for right now. Lou
okay?
stepped away. I think I can't see her. Pretty sure. Yeah, why don't you just go ahead and then we'll check. There's Lou. Okay, cool. Lou's back.
Oh,
Lou, did you have any particular problems you wanted to talk about? Vivian wanted to check in, make sure she's got more questions, but you're here too. Do you have any?
I'm just a little bit confused on the comparison test thing.
Gotcha. Like
Do you know what I mean?
yeah,
Uh,
like how to use it.
Yeah.
Essentially. Okay. Cool. All right, let's take a little detour into that real quick and all right.
oh
So
yeah. So like what's
yeah.
like the difference between like comparison test and limit comparison test?
Okay. Yeah, we didn't talk about the direct comparison test really in class because like I was trying to get a lot of stuff in at the end.
Mm.
So there's two comparison tests. I'll show you. And this is actually good. This is a good thing to know because it'll help you just like intuit more things. So there's this thing called the direct comparison. And here's the basic idea. If I know a series like this converges, and I've got another series where the terms are underneath B sub n, let's say, and usually this is for positive terms. These are non-negative. And then I've got this other series where the A sub n terms are underneath the ones that I know, or they're less than or equal to it, then this series must converge. Converges too. So it's kind of like, let me give you a quick example to make that really clear. So does and it doesn't matter where we're just going to infinity, but does that converge? And it kind of looks like this one, right? It kind of looks like 1 over n cubed. And does this series converge? This one? Does the 1 over n cubed? Yeah, totally, right? It's P series, P equals 3. So P equals 3, so it converges. So then I noticed that, oh, check this out. 1 over n cubed plus 3 is actually underneath 1 over n cubed because you made the denominator bigger. Right? When you make a denominator bigger, you're dividing by a bigger thing, so the fraction goes down. So since this is true for the n values we're interested in, and is that clear that that's true? Because I can demonstrate that, yeah, we're good on that. Okay, cool. Then this series converges. Because when it's underneath a series that does converge. And let me give you another one. Cool. And I am recording this, Lou. So just so you know, this will, if you need to find anything back in here, the recording will be up. And is it okay if I flip the page? We cool? Okay, awesome. So let's take a look at another one. And so this is kind of the divergence one. Does this series where n equals 5 infinity? Let's put a square root. Sorry, let's put square root of n minus 3. Let's use a 3 there. does this series converge or diverge? Well, this one here kind of looks like this one here. Those terms kind of look like just 1 over square root of n. And what do you think about this series? Does this converge or diverge?
Converge.
What was it, Matt?
Converge. Because the P series,
What is P here?
1/2.
Yeah, so that's a diverge.
Oh, sorry. It's like
That's
less
okay.
than
That's
1.
okay. That's a cool. So, because that's less than 1, right? So the P is less than 1. So this series diverges. It's on the other side, right? We've got the harmonic series, and this diverges. And then we've got all the stuff down here, like all the root stuff. And you can just put a little R in there, whatever root you got, that stuff's on this. Actually, I should put it above. So if you've got like the rth root of n, this diverges up here. And then if you have 1 over n to a power p, and p is bigger than 1, then this stuff all converges. So this is like this is your cutoff, that harmonic series, and then roots diverge in general. So look at what I've got here. I've got this thing in yellow that I know when I add those up, they diverge. And I've got this thing in blue that I was given. Notice that this holds true. And this one's a little harder to see, but the thing on the left has a smaller denominator. Think about that. Think about when like n is 25. Right? So when n is 25, the thing on the left is square root of 25 minus 3. This one over here is 1 over square root of 25. So this one over here is 1/2, and this one is 1/5. So like that. Now, let me show you one other way, because it's good to have different ways to think about these things. Surely we would agree that this is true. That the square root of n is bigger than the square root of n minus 3. That seems obvious, right? And then you flip things, and when you flip them, you have to flip the inequality. Like that. It's a bunch of different ways to see that. The key thing here that I'm trying to get across, though, is that since this series diverges, in other words, adds up to infinity, how does this sum compare?
Diverge as well.
It must diverge because it's an even bigger sum because the terms are bigger. Does that make sense? Yeah. Lou, does that make sense to you that this one also diverges? Yeah, awesome. So that's the kind of comparison test we didn't really spend much time on. What we did spend time on was the limit comparison test, and this is the one you're asking about, Lou. So the LCT, limit comparison test, says that if I'm given, let's say I'm given, I'll write this a little different than I did in class. I'm given this series, and want to decide convergence, divergence, but and notice it's like this series. So I've got this one. So like, for example, before when we had like square root of n plus minus 3, that one is kind of like this one here. And notice it's like this. And the thing that you're comparing to is either a P series, it's almost always, or a geometric series. Those are the only things we really understand. Well, like we look at those and you can decide if they converge or diverge. So that's our all our reference points. So then we compute this limit. And it doesn't really matter how you compute this limit. It's basically the ratio of the terms. And if this limit is not equal to 0, then that means when n is really big. So here, let me show you. I can get into this a little bit more. Let's say that this limit is equal to like 3. What that means is that when n is large, because that's what going to infinity means, that a sub n over b sub n is approximately 3. And the bigger n gets, the closer I get to 3. But what does that mean? That means that a sub n is approximately 3 times b sub n. So when n is big, the terms in this one series are just kind of multiples of the other, constant multiples. And so if the one adds up to a finite thing, then the other one's going to add up to a finite thing, just like here 3 times it or something like that. So that's the idea in this test. So we compute that if this limit is not equal to 0, then the series act the same. And so they either both diverge or they both converge. And you already know the answer because you picked the comparison series and it's something you understand completely. So let's do an example of this. Is it okay if I flip the page? Yeah, okay, so I went ahead and did it too fast, but everybody's cool. All right, so let's do an example. Converge, diverge. I'm gonna stop writing that because no shit, that's what we're talking about, right? That's like all we're talking about. So here we have a series 2 to the n over n 3 to the n equals 1 to infinity. Okay, so let's do a little rewrite here, and then I'm gonna actually give you a little bit of time to just think about this. So this is the good rewrite here. It's actually that series. So what does it feel like? And this one's a little tricky. This one's a little bit tricky. What kind of series do you think will compare to a geometric or a p-series?
Geometric.
The geometric. So yeah, geometric with what? With r as what?
2/3.
2/3. Nice. You could also be like, oh, I see that 1 over n, and it looks like, it looks like a harmonic series, kind of. But that 2/3 of the n is actually more powerful here. So let's do that. Let's compare it to, so compare to this series. And see, and just work that test through and see. And I'm gonna run out. I'm gonna be right back in just 1 minute.
Isn't this just the ratio test though? Or it's different?
It looks a little like the ratio test here, but the ratio test doesn't need another series.
Oh,
Does that make
okay.
sense?
Uh-huh.
So yeah,
Yeah.
yeah, but good thinking. It does feel a lot like it. What's cool about the ratio test is you don't need another series. I think this one's going to get us in a little bit of trouble here, actually. And I'll explain why. Is this computation looking okay? Do you see where I got the 1/b sub n, because b sub n is 2/3 to the n. So 1/b sub n is 3/2 to the n. Does that make sense?
So yeah,
You just flip it, just take the
so it'll be
reciprocal.
0 then.
You get
So
zero,
the
is that
limit
what you
will be
said?
0 then.
Yes, because these two cancel. And then this turns into 0. So that kind of, that's okay, but it's a special case of the limit comparison test. So the LCT, okay, let's go back a minute. So sorry, Lou, you were asking for something a little simpler, but we're going to learn more this way. So we're actually, you're going to have a deeper understanding. So we normally have this thing where the limit can't be 0, but if the series you're comparing to converges and that limit is 0, then you're okay. This is kind of a subtle little edge case. Then the original series converges. And I'll actually give you a nice other side of this too. If the series you're comparing to diverges and this limit goes to infinity, then the original series diverges. So these two kind of happen sometimes. Sorry. It happens. It will not happen on your exam. I will promise that. But it's cool to see it. It's nice. We're getting to check out some new territory here. So I'll give you another one. I'll give you another one, Lou, that's like a little bit more like what we want. But I'm going to finish this up because I just like to complete math problems by the LCT, our original convergence. And it's kind of by the LCT special version that we just talked about in here. So let's do one closer to what you're thinking about, Lou. So converge or diverge, and I'm gonna give you this one here. So let's say we've got 2 minus n cubed over n to the 5th plus 2n minus 1, and then we're going to go from 1 to infinity. Does that converge or diverge? And I'm going to say use the LCT. So step 1 is, figure out what is your comparator. So what's our comparison series going to be?
This is probably totally wrong, but is it n cubed over n to the fifth plus 2n?
It's really you're thinking about it the right way. We want to come up with either a P series or a geometric series. So you're getting there. You're definitely getting in the right direction. So that
The
top
P
part,
series?
say that again.
The
Sorry.
P series?
Yes, the P series. It is a P series. And the top is like n cubed and the bottom's like n to the fifth. So remember here, it's just like approximate stuff, and we don't care about multiples or any crap like that. So you were on the right track. Do you see
I
how,
thought that,
yeah,
yeah, I thought that you had to keep every n in there, but you don't. Okay.
no, because when n is really big, which is what
Mhm.
this convergence is all about, that 2n and that, that doesn't even matter when n is a billion.
Okay.
So,
Mhm.
so this is our comparison series. 1 over n squared. Are we agreeing on how things are rolling here? Let me know if you want to talk about any of that, Lou. Happy to. You see where I got this first part from? Yeah, okay, awesome. And once we get that, then this limit, we've been seeing these polynomial limits like all the time, right? The limit of this one, what's the limit going to be on this?
-1.
Yes,
Actually 1, because there's an absolute there.
good job. Good job. You caught it. Yeah. So you notice the top things, like they're both fifth degree polynomials, right? So it's going to be that -1 leading coefficient over the 1, and then catching the absolute value. We get a nice old 1. That's not equal to 0. So these two series act the same. Yeah. Solid, solid. So they both converge. Because we compared to, and I want to be really precise here about the things I'm saying, compared to convergent P series. Oop, n squared. Handwriting's getting bad. Must be this Dr. Pepper I'm drinking here. Little tiny one. All right. Cool. So Lou, does that kind of help with whatever? I don't know if you have any other specific.
Yeah,
Yeah.
and to like just like run things over in my head. So the original comparator was 1 over n squared, and then because it was, we needed to make it less than the original function, we flipped it.
Well, we flipped it because we're looking at the ratio. So careful with the less than, because
Yeah.
we're doing that here. That was
Okay.
the direct comparison, right? So what I was actually doing was taking the ratio of these two things. So there's the top one, and then there's the bottom one. And then
Yeah.
I had to flip them to do that division. That's, you turn that into multiply by the reciprocal. Right, so, oh, squared, sorry. Squared. Do you want me to make that clear?
Oh, yeah, okay.
Yeah, okay.
Yeah,
Okay.
It's like the same in the ratio.
100%, same thing. Exactly. Yep. Cool. What else would you like to talk about? Like, I do have problems to work on. If we can work on problems. Vivian, you still had a couple questions. Lou, you might have questions. Let me just take more of your questions, because that might even spawn other questions that I have for you. So.
Can you look over the series problems that you post on WordClass, like the PDF?
Yeah. Which one? I got them right here. So many problems.
I think it's the first one, like the PDF, and then
We get
problem 4D.
okay. Okay. So it's the one that says series problem 1. Is that the one?
I think so. Yeah.
Yeah, okay. And then
problem 40.
Problem 40. Okay, cool.
Yeah.
Got it. Oh, awesome. Yeah. Oh man. That's a hard one. That's cool. Okay. All right, let's take a look at it. Woo. So we got,
Is that the one that you want to talk to?
I don't know. Let's find out here. Let's just take a minute here.
Okay.
Let's just see. 4 to the n. There's 3 to the n. What's 4 to the n? N equal.
It doesn't look like anything that we've been working on. So
no, I think I was like pushing boundaries here with this one, but what is this one like?
I mean, it's like we can't really do like comparing like P series here.
It's true. We can't.
And then if we do like geometric series, it doesn't. I don't know.
It's not quite those either. Yeah.
Yeah.
I mean, geez, I'm trying to remember. Certainly nothing like this on the exam, but just give me a sec. Just give me one more sec. I forgot what the easy trick is here to do this. Part of me wants to divide through by 4 to the n on top and bottom. Gosh, I don't know. Let's just try. Let's try a comparison test. Let's just see. So we've got 2 to the n plus 3 to the n. And 3 to the n plus 4 to the n. And it kind of looks more like a geometric than anything, right? Because there's the exponent is the moving part. So
What if we write out like first term and second term?
oh, you want to see what it looks like? Sure. So here, this is n equals 1. Is that where it actually started? Yeah.
Yeah.
So 2 to the first plus 3 to the first over 3 to the first plus 4 to the first. Yeah. I don't know. That's not doing anything for me personally. I don't know if you're catching anything out of that. That's not getting me going. I think okay, so when n is really big, let's just think about this. When n is really big, what matters most on top? That's the 3 to the n, right? Because it's just bigger. And then on the bottom, when n is really big, what matters most is the 4 to the n. So let's compare to 3/4 to the n. In other words, this. Just see and see what happens. So with this series, do I expect this converges or do I expect it diverges if that's what I'm comparing to?
Converges?
Converge? Yeah. Did you say, is that what you said too, Lou? Yeah, awesome. Yeah, because it's geometric with r equals 3/4. And so we're expecting convergence. So let's try multiplying by the reciprocal of 3 to the n over 4 to the n. And we're doing our limit. And so the top is 2 to the n times 4 to the n is 8 to the n. Let me write that out. Just using the properties of exponents, you can multiply those two bases together. And then plus 12 to the n over 9 to the n plus 12 to the n. Oh, okay. This is good. This is going to be okay. I think everything's going to be okay. Yeah. So now that limit is funky. We never do anything like that. I'm going to divide the top and the bottom by 12 to the n. So in other words, so I'm going to multiply top by 1 over 12 to the n and the bottom by 1 over 12 to the n. And what I get is 8/12 to the n plus 1 over 9/12 to the n plus 1. Okay, this is okay. Everything's good. Where do these little pieces go in green? Where do those go as n gets bigger?
Infinity.
That is not true.
No.
So let's think. So 8/12, when you square it, you get a fraction of a fraction, right? So when I do 8/12 times 8/12, that gets smaller. Does that make sense? When you multiply 8/12 by anything, it gets smaller because that's just a fraction. So when you do that, smaller, that's smaller.
So it goes to 0 then?
Go to 0. That goes to 0. That goes to 0 because 9/12 is the same thing. And so the answer is 1.
So it'll be 1.
Yeah.
So it converges.
It converges, indeed. Not equal to 0. So by the LCT, it converges. Yes. That was fun.
If this is on the test, I will be so confused.
But you get it now, though, don't you?
Yeah, I get it now.
Well, it won't be on the test. Not for
Okay.
regular credit, anyway.
Good.
No, that's good.
Okay. What else should we talk about?
I actually have to go.
Okay.
So Thank
Oh,
you.
okay.
Thank you.
Oh, thanks, Lou. All right, I'm gonna record the rest and I'll have it up and I'll make
All
sure
right.
you get a link. Did you have anything you wanted to ask before you left and I'll answer it?
Like, just like, is it going to be like the midterms?
It's gonna be more like, it's gonna be like those practice exams that I posted.
Oh, okay.
So make
Got you.
sure,
Okay.
set those down to give yourself, give yourself 2 hours. Take one, pretend it's real. And then I
All
just
right.
put the
Yep.
solutions up earlier, so there's full solutions up for those.
Oh, nice.
Yeah,
All right. Yeah. Thank you.
awesome. Thank you. I'll see you on Wednesday. All right.
See you Wednesday.
Bye.
Bye.
All right, Vivian. Whatever you want to
So
talk
can I ask
about.
questions now?
Yeah.
Can we, so you didn't give out any problems for the Power Series PDF, but,
Oh, I didn't? Wait.
yeah, no.
Oh, I mean, wait, did you say I didn't give out any or we haven't talked about any yet?
Well, because you write out the problems that we should do for
Yes.
each of the PDFs, but
Uh-huh.
not for the racial test one.
Oh, okay. I thought you said the Power Series handout. Okay. Oh yeah, I didn't assign any ratio test ones.
Yeah.
Huh. Well,
Do you want to assign any or?
um, not really. Let's see. Let me look
Okay.
I mean, I think that they're covered under the others. Wait, and I thought I had solutions posted, but I don't seem to have those posted yet, do I?
Yeah. Also, you didn't have the solution yet, so.
Cool. Yeah, let me make sure to get the solutions out here for you, so that you have them. Yeah, that's important. Shoot, I thought I had those posted. I'm sorry about that.
It's okay.
Okay. Oh. Oh, I think it's because you can actually just look them up with the calculators I gave.
Oh, really?
Yeah. So check it out. There's a bunch of different calculators there.
Oh, okay. Yeah, I
and you
haven't
can-
used any because, okay.
No, I
I
mean
was
it's
gonna
good.
save it for,
Don't use them to do them, of course, as you know.
yeah,
But use
yeah.
them to check yourself, right?
Yeah, I was gonna save it until I finish everything.
I mean, if you want more problems, I can add some from that ratio test, if that
I mean, it's really up to you. So
no one else has complained. So
I mean, it's not complaining.
I know you're not. I'm just kidding.
letting.
I'm totally
Yeah, I'm just letting you know.
Thank you. No, that's good to know. I think,
But
yeah, let's not.
can you like go over number 3 on the alternating series?
Sure. Yeah.
Or actually, not number 3. 11. I mean.
Okay. Got it. Okay, so this is on the alternating series handout, number 11. So we're looking at, oh boy. Oh gosh, okay. Luckily it's not the one I thought it was. I was looking at number 12. And I was like, no.
Oh.
So we got this one here.
Yes.
Okay, cool. All right, so we grab the non-alternating part, and that is ln of n over n. Let me make that clear. And so let me ask you, how can I show that's decreasing? Because it is.
So I find the derivatives of it.
Yeah.
And I think I got negative ln of n over n squared. Oh, okay.
You need to use the quotient rule here. Let's go through this together. Let's go through this. So the derivative of the top is 1 over n.
Yeah.
Yeah.
And then
times- yeah.
keep the n and then minus ln of n.
Yes.
And
Times
then
1,
it's
right? Yeah.
yeah, n over n squared.
Perfect.
So the n, the one over n times n is cancelled.
Yes. Yep.
So that I think that whole thing would be negative.
It is eventually it's negative when the top is negative. So the bottom's always positive because it's
Positive, yeah.
but the top is going to be negative when the natural log of n is bigger than 1. And so that's going to happen when n is bigger than e, because the natural log of e is 1. And this is okay. All we need to show is that it's eventually negative forever. And we've shown that. So as soon as n is like 3 or more, that quantity is negative. So you're
So
moving down.
so we'll say that the a sub n would decrease when n is larger than e.
Yes. Yeah.
Okay. And so we would just consider n's for the n values that bigger than e.
Absolutely. And since E is like 2.7, as soon as N is 3 or more, we're good to go. Yeah. So that's tricky. I mean, there's certainly nothing like that will be done, but this is good. You want to know more than the basics, so I like it. So then, what about the limit? So we've got that it's decreasing. What about the limit as n goes to infinity of that term? How do we do that?
So both of the thing goes to infinity, so I just L'Hopital that.
Perfect, perfect. So what's the
And then
derivative?
it would give me limits of 1 over n.
Yeah. Over
And
1,
that
right?
will be just
Yeah, yeah.
1.
Yes,
Yeah.
exactly. So we get 0.
0.
So that's good. So by the AST, this converges.
Do I have to say that it converges only when n larger than e, or
No, because that test really says that as long as this eventually happens and stays that way, that's all that matters. You don't need to get into the specifics.
okay?
Yeah, but it's good that you're thinking like that, for sure.
Yeah, I think that's all. That's all I have.
Is that it?
Yeah.
Okay. Okay. Yeah, and then we need to decide, like, this is like a trickier thing, but if we were going to do condition, I'm just going to show you one more thing. If we take off the alternation, then we've got this series, right? So we could answer the question if we have conditional convergence or not. But this is really, really pretty tricky. Because if I was going to compare this to something, natural log of n is kind of like square root of n, but it's not as fast. So we could compare this to like square root of n over n. In other words, 1 over square root of n. like that. So I think that this would be our comparison series, at least something worth trying.
Mhm.
And that diverges. So the original, I think, also diverges. But I think this problem is tricky in that we have to be a little more clever and use something like n to the 1/4 or something like that. But we don't need to worry about it. Unless you want to do
That'll
it.
be too much for me.
Does that sound like too much for you?
Yeah.
Okay, then let's not do it. Let's not do it. You're in good shape. I don't want to leave you like feeling,
Okay.
yeah, exactly.
I haven't tried the practice exam yet,
Oh, okay.
but I'll
I think
probably
you're gonna be pretty happy with how that goes.
okay. Okay. I'll
You're in
probably
good
gonna
shape.
try it like tomorrow.
Yeah, that's a good idea. Maybe like, I don't know, when do you have finals tomorrow?
Only calc. I
Oh,
have
yeah,
like
right. No, not tomorrow. We don't have calc tomorrow.
oh yeah, right.
Scared the
Tomorrow's
hell out of
Tuesday.
me. Oh my God.
No, I only have like two finals, like calc and chem. That's all.
Okay. Okay, awesome. Very good.
Okay, well,
Um,
thank you for helping.
oh, you're so welcome. Thanks for coming. We wouldn't have had a session if you and Lou hadn't shown, so everybody else can thank you too, because they'll probably, some of them will check this out.
Yeah, be helpful.
Absolutely.
Definitely. Okay.
All
Well,
right,
see you
friend.
on Wednesday then.
Yeah, definitely. Take
Thank
care.
you.
Thank you. Bye-bye.